We've talked about one-dimensional horizontal motion, and we started out with some definitions. In one dimension, I could put a little x here, right? The v average in the x direction is the change in x position over the change in time. And that we just rewrote that, changed our notation a little, and rewrote that as x equals x naught plus v average times time. That was just a little more convenient way for us to write it. It gets the final position in terms of the initial position and the average velocity, but you could use either one. Then we talked about the acceleration. We said it's the change in velocity over change in time. And I haven't put average here, but most of the time we'll be talking about average. This technically is the average, but in most of our examples, we'll be talking about constant acceleration. But strictly speaking, anytime we're taking a value is equal to a change in something over a change in time, we're calculating an average. And so this gives us the final velocity equals the initial velocity plus the average acceleration, once again, times the time. And that means that if we want to know the final velocity, we need the average acceleration. If the acceleration is constant, then the constant acceleration is the average acceleration. Under the conditions where I have a constant acceleration, my average velocity is just the initial velocity plus the final velocity divided by 2. We've done some examples of that, right? Then we took these three equations, the average velocity, the acceleration equation, and the other average velocity equation, and we recombined them and got these equations. X equals x naught plus v naught x times t plus 1/2 at squared, and vx squared is equal to v naught x squared plus 2a times x minus x naught. These, once again, both of these equations assume a constant acceleration because they're assuming this that the average velocity is equal to the initial plus the final divided by 2, and that is only true for constant acceleration. So we're just going to switch gears a little bit here and talk about vertical motion. We're going to do same one-dimensional kinematics, but now we're going to look in the vertical direction. And so we've started out sort of implicitly talking about horizontal directions, which we usually use the x variable for, although I should point out that there is no reason that the x necessarily has to represent the horizontal direction. And as you're going to see, when we change x's to y's to do vertical motion, our equations are going to look just the same. So if we want to rewrite this for our y motion, where we're using y for the vertical direction, we would write it as y equals y naught plus v average in the y direction times time. Similarly, this one will become vy, the final y velocity, is equal to v naught y plus the acceleration. And this time we might put a little y here times t to let us know that, and maybe I could stick a little x down here to let us know that this acceleration that we're talking about is the y direction acceleration, not the x direction acceleration. Eventually there'll be times where we're using both. We get an acceleration in the x and y direction when we're doing two-dimensional kinematics. And so then I can say v average y is equal to v initial y plus the final y velocity divided by 2. Similarly, here I can say y is equal to y naught plus v naught y times time plus 1/2 a sub y times t squared. And finally, vy squared is equal to v naught y, is equal to v naught y squared plus 2a sub y times y minus y naught. And again, if I want to be careful, I should put little x's over on these accelerations to remind myself that those are accelerations in the x direction and these are accelerations in the y direction. So as you can see, there's really not much difference between our vertical equations and our horizontal equations, but we'll generally try to use y's for vertical motion and x's for horizontal motion. As we'll see later, you can't always do that. So now we're going to look at a special kind of 1D vertical motion. It's vertical motion, which we call free fall, and this is objects that are just moving under the influence of gravity and nothing else. So it's an object that maybe you drop from the sky, or you throw a ball straight up in the air, or something like that. We're going to neglect a lot of things like air resistance, and the fact that gravity gets weaker the farther you get away from the Earth, and the fact that the Earth is curved, and all of those little subtleties, which we'll address maybe a little bit in class, but mostly in later classes. But we're going to write down the equations we have here. These are kinematic equations for vertical motion, with the constraint that the only acceleration we have is minus 9.8 meters per second squared. That's what our acceleration in the y direction is always for free fall. This is just gravity. And so what we do is we use the constant g, and we say g is equal to 9.8 meters per second squared, and it's downward, and so we would say our a sub y for free fall motion is equal to minus g, because g is positive 9.8 meters per second squared, and usually we're picking up as positive, and so in order for things to accelerate downward, we have to put a minus sign out here, and we always put it outside the constant. We don't set the constant g equal to minus 9.8 meters per second squared. We set it equal to 9.8 meters per second squared, and then we put the negative sign there. And so I'm going to rewrite all of these equations with, instead of a sub y, with minus g. And so the first one doesn't change. I just get y equals y naught plus v average in the y direction times time. I may have trouble squeezing them all in. I get v sub y is equal to v naught y, and instead of plus a sub y, I have minus g times time, because I replace my a sub y with minus g, right? Similarly, I get v average y, this one is unchanged, is equal to v naught y plus vy divided by 2, right? And then I get y is equal to y naught plus v naught y times time minus 1/2 g times time squared. In other words, I replace the a sub y with a minus g. This equation is exactly the same thing as the x equations. I've just replaced all the x's with y's, and then I've replaced the acceleration for the y direction with a minus g. Similarly, for this last one, I get v sub y squared is equal to v naught y squared minus 2g times y minus y naught. Right? And so for free fall motion, these are my equations. And so you might just want to write these down unless you can just remember that simple substitution, right? I could say free fall. They look exactly like our other equations, except I've replaced the x's with y's, and I've replaced the a sub y with minus g. So let's do an example. Suppose I throw a ball vertically at 40 meters per second. I couldn't actually throw it that hard vertically, but maybe I could shoot it out of a cannon or something. We're going to ask, what are its position and velocity at 1 second intervals after it leaves my hand? Now we can go back on our previous sheet and we can find an equation for the velocity as a function of time. And we say Vy is equal to V naught y minus g times time. And then we've got two equations we could use for position. We could say y is equal to y naught plus V naught y times t minus 1/2 gt squared, or y is equal to y naught plus V average y times time. To make the math on this problem a little easier, we're going to use g equals 10 meters per second. We'll do that in most of our examples in class because it only introduces a 2% error from 9.8 meters per second squared. And so it's pretty easy to manage. I'd recommend on your homework, especially the online stuff, that you use 9.8 because the program is set, I think, for a 3% correction lenience on your answer, and it's easy to get off of that if you make a few small adjustments. And so I would go ahead and use 9.8 on the homework. And so, we'll continue this on the next page, but these will be the equations we'll use, and I'll talk about how we get the position and the height on that page. So here's a projectile problem that we're just talking about. In this example, first of all, I'm going to use g equals 10 meters per second squared, so we can do a lot of this stuff in our head. We know that our initial velocity is 40 meters per second because that's how we threw it up, When it left our hand, it was going at 40 meters per second. And so we say that at that position, at that time, the y position is 0, or this is just our initial y, right, which we're going to set equal to 0. Similarly, at t equals 0, we also have, we know the v sub y, it's just the same thing as our v naught y, and so that's 40 meters per second. I'll put the units up here. This is in meters per second, right, and this is in meters, so I don't have to write the units in there. And so now we know at t equals 0, our velocity is 40 meters per second, positive, so that means it's going up, and our position is 0, right? And so now we want to know what it is at 1 second. Well, at 1 second, the y velocity, if we look at our y velocity equation, is v sub y is equal to v naught y minus g times t. Well, g is 10 meters per second squared, and time is 1 second. So it's 40 meters per second for our initial y, minus 10 meters per second squared times 1 second, or 30 meters per second, right? That's at t equals 1 second, right? And now we can say, look, our y, let's come down here to this last equation to figure out our position, right? Our y down here is y naught, which is 0, plus my average y velocity times my time. Well, my average y velocity is 40 plus 30 divided by 2, because the acceleration of gravity is constant. It's always 10 meters per second squared. And so this is 40 plus 30 divided by 2 is 35, right, times 1 second, or 35 meters. Right, my average velocity was 35 meters per second times 1 second. Similarly, at 2 seconds, right, I can say, well, now my y velocity again over here, right, is my initial velocity minus g times 2 seconds, right? So it's 40 minus 20, which is 20, right? And so you can kind of see a pattern here. After 3 seconds, I have 10. After 4 seconds, my velocity is 0. What's the ball doing when it's at 0, when its velocity is 0? At 5 seconds, this becomes 40 meters per second minus g times 5 seconds. That's just minus 10 meters per second. Similarly, 6 is minus 20, 7 is minus 30, and 8 is minus 40, right? And so I can just use this equation now, my average velocity times time, to get my position, right? And if I look at the 0 to 2 interval to get this guy, my average velocity over that was 20 plus 40, right? The initial plus final divided by 2. That's my average velocity between 0 and 2 seconds, which is 30 times 2 is 60 meters, right? Similarly here, I can say my average velocity between 40 and 10 is 40 plus 10 divided by 2 is 25, times 3 is 75, right? Similarly here, I can say my average velocity over the first 4 seconds was 40 plus 0, initial plus final, divided by 2, which is 20, times 4 seconds, or 80 meters. So if you notice, in the first second it went 35 meters, and then it went 25 meters, and then it went 15 meters, and then it went 5 meters. It's constantly slowing down, which you see in its velocity in the next column over, right? Now 40 minus 10 is 30, divided by 2 is 15, right? Times 5 seconds, back to 75 meters. 40 minus 20 is 20, divided by 2 is 10, times 6 is 60. And so on. This guy is 35, and this guy is back to 0. And so the object is going up, and at each second is at 40, 30, 20, 10, 0, minus 10, minus 20, minus 30, minus 40. And its position in that time, it's going up for the first 4 seconds till it gets to the very top of its trajectory at 80 meters, and then it starts falling back down and goes all the way back to 0. We could also have used the middle equation to calculate the object's position, and if we do that at any particular time, we could say we did it at 4 seconds, right? Its initial position is 0. It's at 4 seconds, its initial velocity is 40 times 4 is 160, minus 1/2 times 10 times 4 seconds squared. 160 divided by 2 is 80, and so 160 here minus 80 gives me 80, and that's the If you plug into any of these equations with the correct times and initial velocity, you will get this row, the position row, just like we calculated with the third equation.